this, and this. And okay, so guys, if I believe that we're done with this, which then means we're ready to move along and talk about things that you don't yet understand about equilibria. So guys, actually, you know what? Maybe we should focus in here for just a second. So let's make sure we're clear on this idea, because this is, I think, where we wrapped up last time. So guys, what we said is this. If we've got a balanced equation where we've got reactants and products, we can write a Kc value. And a Kc value is a product to reactant ratio that is the ratio of concentrations at equilibrium raised to exponents, and the exponents are the coefficients from the balanced equations. And remember, guys, when we talked about this last time, we stumbled a little bit over the idea as you were trying to connect this to rate laws, and somebody even said, wait, does that make this an elementary step? And then we realized that that question really wasn't meaningful, because we're not talking about rates of reaction, we're talking about concentration ratios when the rates become equal at equilibrium. So this has nothing to do with elementary steps. This has nothing to do with rate. This is all about representing the concentration ratios that exist at equilibrium. You okay with that idea? Okay. So guys, with that said, now let's get into the new stuff. So not only can we Kc values, what does the C stand for? Concentration. So guys, we can write Kc values, but it turns out we can also write equilibrium expressions for gas phase reactions. And I'm realizing this might be a good time to orient you to your AP equation sheet. So guys, grab your equation sheets. Does anybody need them? You guys all have them? Wow, first time all year. All right. That's all right. I know, right? So guys, if you look at the page 3 side of the equation sheet, you'll notice that it says equilibrium, which is all about what we're talking about. And they give you right up front exactly what I just took off the screen. Kc is equal to C's raised to C, D to D, and then they give you the balanced equation. They lay it all out there for you, right? Okay, so then guys, if you allow your eye to glance below at the next equation, you'll notice that there are no longer brackets in the equilibrium expression. What do the brackets represent? Molarities, right? Concentrations. Well, guys, this is what we're going to talk about now. It turns out that if you've got a reaction that is in the gas phase, you can actually write what are called Kp expressions. So now, rather than a molarity ratio, what we've got is a partial pressure ratio. So these are not called Kc's because they're not concentration ratios. They're called Kp's because they're pressure ratios. But guys, it goes exactly the same. If A and B and C and D are gases, then we can identify the equilibrium mixture by simply saying the partial pressure of C raised to the exponent of C. Oh, there should be an equilibrium arrow in there. I don't know where it went. Hold on. Let me go back here. Grab this. Is that the same? Yeah, we're okay. All right, so there we go. So guys, now we've got a gas phase equilibria, and the idea is that C and D are still our products, A and B are still our reactants, W, X, Y, and Z are still our coefficients. Notice on the AP cheat sheet, it's lowercase a, B, C, and D, I think, isn't it? Yep. But regardless, guys, now what we're doing is instead of using concentrations, we're using partial pressures. Yeah, and so So I'll explain it, but don't get too caught up in this. So guys, why are we able to do this? Well, remember that day during the gases unit when we talked about PivNert and we solved this for pressure and we got this? And then we said that a mixture of gases would be number of moles of A, then number of moles of whatever gas 2 was. Do you remember this, Brandon? And then we said the idea that R's are the same, T's are the same, V's are the same. And so there's a direct relationship between pressures and numbers of moles. But numbers of moles is related to molarity, right? It's moles divided by liters. So if there's a number of mole to pressure ratio, you would expect that the ratio of moles of product to moles of reactant would have a similar ratio to pressure of product to pressure of reactant, because there's a pressure-mole relationship that underlies all of this, and that's why it's allowable. Now, guys, I'm not sure if I took this out of my notes. I may just ditch this. Yeah, so you know what? Let me just lay this on you. You will not see this in homework. You will not see this in the test. But guys, it turns out that you can, for reactions, calculate a Kc value and a Kp value for the same reaction. So now you're going, how on earth do you do that? Well, guys, the way that you do it is this. So in order to come up with Kp, you need to know the pressures of each one of these, right? But if you know the pressure, you can convert to moles using PivNert. And if you know the number of moles, you can divide by the volume of the container, and that gives you something like molarity. Does that kind of make sense? So it turns out that what you can do is, for a gas phase reaction, it's easy to calculate Kp. They just give you the partial pressures. But then if you take those pressures, convert them to moles, and then divide by the volume of the container, you then end up with something like molarity, and from that you can calculate Kc. Well, guys, it turns out that those values are typically not the same. Now, on the old AP format, they used to give you the equation that allowed you to convert Kp to Kc. I think it's still in the book. Do any of you have your, can I look at your book? I think it's still in here. And I can give you the page number if you want to look at it. But guys, it's not, did you find, oh, no. But guys, you don't need to worry about it because it's not on the AP stuff anymore. It's at the bottom of page 617. So, I mean, I don't know. If you're curious to see the equation, you can look it up. But guys, frankly, it doesn't matter because you don't have to do that anymore. It's possible, but there's nothing significant to be learned from it. You guys okay? Okay, so now guys, let's do this. Whether it's a Kc or whether it's a Kp, you have got to learn to unpack the information that is contained within a K value. And guys, this is going to be wildly important in the next unit. You've got to be able to look at the K value for a reaction and immediately understand what is going on with that reaction. So guys, in order to make sense of all of this, you got to understand this. Which one's right? Are K values products divided by reactants or reactants divided by products? Products divided by reactants. And so guys, because that's true, because these are products divided by reactants, everything that you're about to learn then makes sense. So guys, first of all, magnitude. The magnitude of Kc tells you the direction that a reaction proceeds. So guys, let's just do this logically. So we've got a reaction where reactants are turning into products. And we know, you know what, let me clean this up. So we know this. We've got reactants turning into products, and we know that our K value is products divided by reactants. So guys, let's talk magnitude. What do you know about a reaction if your K value is larger than 1? What does that tell you? Do you have more product or more reactant? More product. And if you've got more product, which direction does this reaction tend to go? To the right. And we say that this reaction favors products. Does that make sense? Now, guys, let me ask you the other. What if the reaction favored reactants? What would your K value be? Less than 1 or negative? Less than 1. Guys, can K values be negative? Why not? There's no such thing as a negative concentration or a negative pressure. You can't have less than none. So guys, remember the range of values then. Your K values, just a second, range from 0 to huge, and the important point is 1. And really maybe 1 should be more like in the middle. So if you have a K value smaller than 1, that means that your denominator is bigger and that reaction favors reactants. And then if you have a large K value, the reaction favors products. So what does large look like? Well, guys, typically your K values actually kind of range like this. So if this is 0, big is like bigger than 10 to the third. And small is typically smaller than like 10 to the negative fourth. Wait, that shouldn't be 0. That should be 1. Sorry. So guys, when we say big, we mean big, bigger than 1,000. And when we say small, we mean small, like smaller than a 10,000th. So very seldom will you see K values that lie in this range. They tend to be off the charts in either direction. Yeah? No. So I thought I wrote it on there. It's actually science resale. Okay. Yeah, I put them in there. Yeah, what? So we'll deal with that. For right now, you just need to understand bigger than 1 favors products, smaller than 1 favors reactants. So guys, summarizing all of that, let me give you this. So if Kc is large, the reaction favors products, and we say that the equilibrium lies to the right. Similarly, if Kc is small, and again, guys, that means less than 1, but not less than 0, then that reaction favors reactants, and the Kc lies to the left. I'm sorry, the reaction lies to the left. What? But you won't see that. They won't give you a negative Kc value and go, what does this mean? No, that's way too elementary. Yeah. But guys, what about if we do this? This is interesting. So we've established that if reactants turn into products, then Kc is products divided by reactants, right? You okay with that idea? I'm surprised you guys didn't correct me. Shouldn't that always be a double-headed arrow? Yeah. You okay with that idea? Now, guys, what if this happens? What if we switch them? What if we change their names? And what if we say the products are now our reactants and the reactants are now our products? If we flip the reaction over, what does that do to Kc? It inverts it. So this would be, just a second, this would be 1 over Kc. So guys, if you just arbitrarily switch the reactants, so for example, if you had N2, or if you had N2 plus 3H2 in equilibrium with 2NH3, by the way, what do we call that? Haber process. And if we found the Kc value for that, and then if we came along and if we did this, what does the Kc value become? And it becomes the inverse. It's 1 over Kc. Because you're flipping the reactants and products, you're flipping the Kc value, which is 1 over Kc. Talmadge, go ahead. No, because great question, right? So here's the idea. So what does it mean to be at equilibrium? So let's talk about not yet at equilibrium. Guys, hold on. Let's make sure you heard. Guys, Talmage's question is very important. I love that he's tying this back to spontaneity. And he said, wait a second, if a reaction is only spontaneous in one direction, can you just arbitrarily flip this thing over? So let's talk about it. So do you understand the question? Because the answer is important. You okay? Okay, so guys, the idea is this. What does it mean when we say the equilibrium lies to the right and the equilibrium lies to the left? And how does that relate to spontaneity? So the idea is this. Say that we're talking about the Haber process. And when we start this reaction, we start with a bunch of reactant and that turns into product, right? So the equilibrium is progressing to the right. Now guys, could we also do this? Could we also start with a bunch of product and would it then turn back into reactant? Yes or no? Does that happen? Okay, so let me offer you this. Hold on a second. Does that, oh, not that one. Does that happen? Does it matter where we start? Does it matter if we start with a bunch of nitrogen and hydrogen or a bunch of ammonia? It does not. Guys, we talked about this. You understand, we saw this slide before. We saw this on Monday. Monday? No, what's today? Wednesday? When did we see this? Friday. Okay, maybe you don't remember. So guys, is it coming back to you, the significance of what we're looking at? So guys, the idea is this. I'm going to zoom out so that I can write. So what we've got here is the Haber process. And the idea is here we start with a bunch of H2, a bunch of N2, and no NH3, and it falls to equilibrium like this. Then guys, here we start with a bunch of NH3 and no N2 and no H2. And guys, at equilibrium, it falls to this. And what did we say about those two equilibria? They lie in the same location. So guys, now we need to distinguish this idea of going to equilibrium and at equilibrium. And so Talmage brought in this idea of spontaneous directions. So let me go back to the slide that we had up before, which was, I guess technically, was it this one? Yeah, it was this one. But then guys, we had this mess to talk about. And so guys, the idea, is this too messy to really read, or are we okay? Are we okay? Okay, so guys, the idea is this. Imagine that we start the Haber process with a bunch of this and no product, no NH3. Which direction will the reaction go? To the right. So this becomes the spontaneous direction because we've got a pant load of this and none of that. Now guys, imagine that we start the reaction and we've got a bunch of this and none of this. Now which direction will the reaction go? It's going to go the other way. So now the question is, what does that tell us about spontaneity? Well guys, think about what you learned way back when we talked about thermochemistry. When a reaction is at equilibrium, which direction is it going? Both, yes, both directions simultaneously. So which direction is the spontaneous direction? Both of them. So guys, equilibrium reactions do not have spontaneous directions. It doesn't mean they're not spontaneous. It means they're spontaneous in both directions simultaneously. So what determines the direction the reaction will go? And the answer is the relative amounts of reactants and products. If you have a bunch of this, it'll go this way. If you have a bunch of this, it'll go that way. So equilibrium reactions don't have a spontaneous direction because they're spontaneous in both directions, and the direction that they will go is simply the direction they have to go in order to get back to that equilibrium ratio. Does that make sense? Is that okay? So as a result of that idea, it doesn't matter which we call the reactant or the product. We could switch these arbitrarily because they're going to go in both directions. You guys good with that idea? Is that okay? You're sure? Again, I'm not sure if you're just glassy-eyed because you get it or glassy-eyed because you're confused. You guys okay? All right. So, and then guys, we said this. We said that if we flip the reaction, Kc is the inverse. You guys good on that? Go ahead.
So you said like the Kc value is large,
Yes. Yep.
But at equilibrium, we'll do the equilibrium Kc is equal to 1, but it wouldn't favor one side of the reaction, but it because those are like the perfect ratios where it should be.
Let me, I don't know if this is what you're getting at, Rebecca, but let me try to take a swing at what you're saying. So imagine this. Would it be better to do hypotheticals or do like the Haber process? Let's do hypotheticals. So say that we've got A plus B in equilibrium with C and D. Okay, so, and let's say that the Kc value for this is like 1,000,000. It's big, okay? So what does it tell us if the reaction has a Kc value of 1,000,000? We're going to have a bamboozle of C and D and not much A and B, right? So if the Kc of this is, let me think about, so if we write it like this, we've got C and we've got D and we've got A and we've got B, and if this number is like 1,000,000, then we're going to have huge amounts of this and very, very little of that. Is that okay? So once it settles into equilibrium, this is where it's going to end up. Now guys, understand that that doesn't tell us how it got to equilibrium. We could have started with all A and B and no C and D. We could have started with all C and D and no A and B. We could have started with a lot of this, a little of this, a lot of this, a little of that. It doesn't matter where you start. That reaction, because it's spontaneous in both directions, is going to go to where that equilibrium lies, which we're representing as 1,000,000. Okay, now, what if we have 1,000,000 times more this than that, plus a little extra? What if we have 10,000,000 times more? Well, then the reaction's not at equilibrium anymore. So what does it have to do to go back to equilibrium? Well, it's got to use up a little bit of this and make it back into that. And that will tell us which direction the reaction will go. So the Kc value tells us where it's at equilibrium. And then, given where it's actually at, we can figure out which way it'll proceed. You're going to find out that's how we're going to finish the day. It's what is called a Q value, a reaction quotient. And so did that get to your question? Was that okay? And so guys, everything that I just discussed with Rebecca and with all of you is actually the last thing we're going to talk about today, which is called a reaction quotient or a Q value. So right now, here's what we know. Kc's describe where the reaction is at equilibrium. It doesn't matter how it got there, but if it's not there, it's going to head there no matter which side of equilibrium it's on. Okay? Are we good with that? Okay. All right. So guys, with all of that said, then let's talk about now, and this is going to be really important moving forward. Guys, let's talk about the different types of equilibria. Now again, there's the possibility for confusion here because we talked about homo and heterogeneous catalysts, right? This has nothing to do with that, but they are homo and heterogeneous equilibria, and the definitions of homo and heterogeneous are the same. So what does homo mean? Same phase. Hetero means different phases. So guys, in the same way that you can have homo and heterogeneous catalysts, you can also have homo and heterogeneous equilibria. So guys, write this stuff down with me because this is gonna trip you up on for the rest of the year. you're going to forget about this and it's going to kill you. So guys, homogeneous equilibria are equilibria where all of the substances are in the same phase. Every single one. For example, the Haber process. Hydrogen gas, nitrogen gas, ammonia gas. They're all gases. Now guys, there's also heterogeneous equilibria where the substances involved are in different phases. This is where this gets painful. That was actually the thing that Haber did that was brilliant, was he figured out a way to make it a heterogeneous equilibria by liquefying the ammonia. At standard temperature and pressure, the ammonia that's created is actually a gas, and that's what made it hard to collect. So he figured out how to tweak the pressure temperature conditions just right to get it to liquefy, and then you could siphon it off and dissolve it in water so it wouldn't go away. Yeah, pretty smart. So, guys, let me introduce you to the craziness of heterogeneous equilibria. You ready? Guys, do this. Write the Kc expression for the reaction that takes place between potassium iodide and lead 2 nitrate. Sounds familiar? Yeah, right. You're still going to screw this up, but at least it's familiar. So for you, Valeria and Rachel, guys, we actually just did this reaction in lab, many of you today. So guys, do this. Write the Kc expression for this reaction. I need you to have the experience of failing at this. Guys, do this. Because if you fail at this once, hopefully you won't fail at this when it actually matters. It actually is. Yeah, so good. So guys, good question. Mark is saying, wait, is that an equilibrium process? And guys, it turns out that the lead 2 iodide that's formed does slightly dissociate. Lead 2 iodide is not completely insoluble in water. Some of it, not much, but some of it actually does break apart and go back into its original ionic state. So it is an equilibrium process. And guys, you're going to find out in chapter 17. In chapter 17, when we start talking about slightly soluble salts, a lot of the things that you thought were insoluble in water actually do in fact dissolve a little bit. So little that we really don't care about it, but technically they do dissolve a little bit. There are very few salts on this planet that are actually completely insoluble. Bubble thoroughly bursted. Did you guys get it? Okay, so let's write our... Oh, you did. I'm just trying to figure out when to show you what you did wrong. I'm just gonna... We'll save the problems for later. So guys, first thing we need is a balanced equation. So we've got Ki, we've got Pb, NO3 2, and double displacement reaction. We've got Pb, I2, and K, NO3. And so to balance this, 2 there, 2 there. Am I good? You good? We okay? Okay, so now guys, writing the Kc expression, Kc is equal to products, PbI2, and KNO3, And what happens to that coefficient? Becomes an exponent. And then, guys, we've got Ki. I know I'm in the way. I'll move in a second. And that is squared. And then lead to nitrate, like so. You guys okay? Did y'all come up with this? You shouldn't have, because it's wrong. So, guys, let's talk about why it's wrong. In order to talk about why it's wrong, what I need you to do, and you didn't have to be in the lab to know this, because we've done solubility rules. Guys, let's go back to our balanced equation, and let's put subscripts on our substances. So potassium iodide, does it dissolve in water? Yeah, so that would be aqueous. Lead nitrate, does it dissolve in water? Yes, so that would be aqueous. Now, guys, lead iodide, lead 2 iodide, does it dissolve in water? It does not. It is a solid. And then, guys, potassium nitrate, does it dissolve in water? Yeah, all nitrates dissolve in water. So, guys, now that we've put the subscripts on this, let's contextualize this. Because, again, this is the reaction that you did in part 3 of your lab. And you may remember that this was 0.1 molar and this was 0.1 molar. Those things have molarities, they're aqueous, you got them delivered to you in their aqueous forms. So that's all good. So now do you see the problem with our Kc expression? Say it again. It's actually not assumed to be 1, but you're on to it. Guys, the problem is right here. This is a solid. Now, guys, if you look at my Kc value, what kind of numbers go in these brackets? Because they're brackets, molarities, concentrations. And guys, by definition, what is the concentration of something that doesn't dissolve in water? Or we should say it this way. What is the concentration of something that isn't dissolved in water? It's 0. And if you leave that there, and if the value of this is 0, what happens to the value of the entire expression? It either becomes 0 or undefined, depending on if it's in the numerator or the denominator. So guys, what do we do with that? Well, this is the solution. You don't have to understand why this works. I'm not going to try to explain it to you. You just have to understand the practice. Guys, the problem that we've got is this. This is a solid. By definition, that solid is not dissolved in water. Because it's not dissolved in water, it doesn't have a molarity. Because it doesn't have a molarity, it does not belong in the Kc expression. So the Kc expression for this reaction is actually just KNO3 squared divided by potassium iodide squared times lead 2 nitrate. So guys, the bottom line is this. You exclude solids from Kc expressions. Why do we exclude solids from Kc expressions? Because they don't have molarities. But guys, it doesn't stop there. You also exclude liquids. Let me show you. If you don't understand what I'm talking about, check this out. Hydrogen gas plus oxygen gas produces water. And guys, this isn't actually an equilibrium process, but pretend that it is. So this is a gas, this is a gas, this is a liquid. So now we say we write a Kp expression for this. So we would say the pressure of water squared, the pressure of H2 gas squared, and the pressure of O2 gas. Now when we go to plug in values, what is the pressure of liquid water? 0. It's a liquid and not a gas. See what I'm saying? But guys, no. It's not right. They're partial pressures, but liquid water doesn't have a pressure. It's not a gas. It's a liquid.
Right. What about molarity?
And we're not talking about molarities.
The Kc value that we did for the potassium iodine and the lead nitrate was, it wasn't partial pressure.
No, these were molarities.
Yeah, but it's
So guys, let's summarize it like this. We've got two types of equilibria that we write. We write Kc's that need concentrations. We've got Kp's that need pressures, right? So now let's do this. Imagine that we have a reaction that creates a solid. What is the concentration of a solid? 0. What is the pressure of a solid? 0. Imagine that we have a reaction that creates a liquid. What is the concentration of a liquid? 0. What is the pressure of a liquid? 0. So guys, the idea is this. When you are writing K values, be they Kc's or Kp's, you never include solids or liquids in the Kc or Kp expressions because solids and liquids don't have concentrations or pressures. So, I summarized that like, just a second, like this. So guys, bottom line is this. When you're writing Kc's or Kp's, we do not include factors for pure solids or pure liquids. Why not? Well guys, fundamentally, while these things are needed to reach equilibrium because they're reactants and products, their concentrations or pressures don't change. They don't have concentrations or pressures. Therefore, they do not get included in the equilibrium expressions. Go ahead, Tim.
so aqueous solutions do have concentrations with pressures?
No, but you would not be writing Kp's for aqueous reactions. Yeah, but no, they don't. Or at least if they do, we don't care. We don't think of them that way. I mean, technically, the solvent could be off-gassing, but we don't care. So guys, what does this have to do with what we just talked about? Well, guys, realize that what we just talked about relates back to heterogeneous equilibria. Because what we're talking about is gas or aqueous reactions that create solids or liquids. There's your change in phase, and that change in phase comes back to the idea of heterogeneous equilibria. So if you've got a heterogeneous equilibria, the chances are good you're either creating a solid or a liquid. And those solids and liquids do not show up in your Kc or your Kp expressions. Because that's the idea, that because they're pure, they aren't something dissolved in something else, and as a result, they don't have a molarity. Would you feel better if I got rid of pure?
I mean, I'm just wondering, like, if there is a...
No, there's no distinction. Yeah, don't. Go ahead.
So the example we had earlier was that H2O2 is spontaneous
Hold on a second. Where'd it go? There. No. So what would, well, yeah, but the one is understood. So what would the Kp for this look like? So this part's gone. Oh, yes. No, I'm sorry. Yes, because this is in the denominator, it would be 1 over this stuff.
So we treat all solids and liquids in these equations as one.
You treat them as not yeah, so in this case, you'd have to put the 1 for a placeholder, but honestly, the things that we're going to see is that these things will typically show up on the other side of the equation and they just drop out. So you'll see. So, you guys okay with the concept? We got one more thing to talk about and we're done for the day. You good? Okay. So guys, let's set the stage for what we need to talk about now. And this is coming back to what Rebecca got us thinking about as we were talking about Kc values. So the idea is this: if we've got A plus B, and that's in equilibrium with C and D, and we write the Kc, and it's C, and it's D, and it's A, and it's B, the question is this: what numbers go in those brackets when we go to solve this? What kinds of numbers go in there? Concentrations when? When they're at equilibrium. Does that make sense? So guys, the numbers that go in the brackets are not just concentrations, they are concentrations when this reaction is at equilibrium. You good with that idea? Okay, now guys, what about this? So yeah, Kc is understood to be at equilibrium. And when it's at equilibrium, we have a ratio of products divided by reactants. That we understand. But guys, here's the trick. You don't have to plug equilibrium concentrations into this expression. In order for it to be a Kc, those have to be equilibrium concentrations. But guys, understand, we can still use this product divided by reactant ratio at conditions that aren't at equilibrium. But when we do that, it's no longer okay to call it Kc, so we call it Q. So this is what we're now going to talk about. So what is Q? Q is the same product divided by reactant ratio, but now we're going to plug in concentrations that aren't at equilibrium. Does that make sense? So let's summarize that if you want to write this down. So guys, the topic for your notes is this. These are what are called quotient, Q-U-O-T-I-E-N-T. These are what are called reaction quotients. So guys, a reaction quotient is simply Q. And what is Q? Q is Kc at non-equilibrium conditions. So you may want to scratch that down. Q is equal to Kc at non-equilibrium conditions. And Q is named the reaction quotient. So guys, the question then becomes, who cares? Right? I mean, why is this important to us? And you're going to find out, especially in chapter 20, when we're doing electrochemistry, this is going to be wildly valuable to you. So guys, let me explain to you why this is wildly valuable by showing you sort of a fictitious, a non-real world, a fictitious example. And then we'll make this make sense, and I think it'll all come together for you. But I find this is the best way to teach it. Rather than show you notes, let's just play with some numbers and see how this goes down. So guys, why do we care about Q? Well, check this out. Do this with me. So we've got a simple reaction where products, where reactants are in equilibrium with products. Okay, so you ready? Here's how this goes. I'm trying to decide if I want to put this in a table or not. I don't think I'm going to. So guys, say that we allow this equilibrium to come to, we allow this reaction to come to equilibrium, and at equilibrium, so I'm just going to write that here. So at equilibrium, we find out that the concentrations, and I'm just going to make up some wild and yet easy numbers to work with. So at equilibrium, this is 10 molar and this is 2 molar. What is Kc? 5, right? Products divided by reactants. Kc is equal to products divided by reactants is equal to 10 divided by 2 is equal to 5. You good with that? Okay. Now, guys, say that we come along and we set up this reaction again. But now what we're going to do is we are going to take this reaction away from equilibrium. So say that we take this reaction and what would be a good combination of numbers? Let's say that we set up this reaction again, products on top. So now let's say, I'm debating on whether I should write this on a side. I'm just going to write it off to the side. So say that we set up this reaction. Maybe I'll rewrite it. That might be better. Okay, so now we're going to set up this reaction again, and we're going to have the equilibrium between reactants and products. But now let's say when we set up this reaction, we set this thing up, and we've got a concentration of products of 30 and a concentration of reactants of 2. No, and that's my next question. Is this reaction at equilibrium? How do we know that it's not? Well, let's do some math. Guys, what is Kc equal to? Products divided by reactants. So now let's plug in our numbers. Products are 30, reactants are 2. What does that equal? 15. So how do we know that this reaction is not at equilibrium? Because this number is not that, right? Just a second. At equilibrium, Kc is going to equal 5. If you plug in concentration numbers, and if it doesn't divide out to be 5, then this reaction is not at equilibrium. So is this number a Kc value? No. What kind of value is it? This is a Q value. But just a second, I'm going to ignore you for a while, Rebecca. You got to let me roll. Okay, so guys, are you comfortable with the idea that what we're doing now is we're looking at this reaction in another set of conditions, and now we know the reaction is not at equilibrium? Let's make sure you're clear. How do we know this isn't at equilibrium? Because it's not 5, it's not Kc. So we now know that this isn't a Kc value, it's a Q value, because Q is just Kc at non-equilibrium conditions. So now let's answer the big question. Who cares? What does Q tell us? Well, guys, here's the idea. Let me underline these so they stand out. So there's our equilibrium, our concentrations. At equilibrium, it's 10 to 2. At these conditions, it's 30 to 2. So do we have too much product or too much reactant? We've got too much product. So guys, if you think about our tube demonstration, it's as if I dump more product into the left-hand tube, the right to you. If I dump more product in this right-hand tube, it's sort of analogous to this. But here's the question. If we've got too much product, and we do, if we've got too much product, what does this reaction have to do to get back to equilibrium? It's going to make more reactant, and the reaction is going to go in this direction. Guys, we just said something very important. Over here, which is bigger? Q, remember this is, let me switch back to blue. This is Kc. So which is bigger, Q or Kc? Q. And if Q is bigger than Kc, which direction will the reaction go? To the left. Chew on that for a second. Q is bigger than Kc. And when Q is bigger than Kc, the reaction will proceed to the left. Now guys, how are you going to remember that if you don't have these scribbles in front of you? What does it mean that Q is bigger than KC? In order to make Q bigger than KC, do you have too much numerator or too much denominator? Numerator. You got too much numerator. And what's in the numerator? Products. So if you've got too much product, the reaction's going to go to the left to turn it into reactants. So guys, now we have a guiding principle. If Q is bigger than KC, you've got too much numerator. You've got too much product, so the reactant's going to get rid of product, turning it into reactant, and the reaction will go left. It now it will move toward. It doesn't mean that the equilibrium is shifted. The way that we say it is the reaction will go to the left, or the reaction will create more reactant in order to reach equilibrium. Now, guys, what if the other was true? What would be a better way? So now Q and KC, and now what if KC is bigger than Q? What if Q is too small? If Q is too small, what do you have too much of? Denominator. You've got too much reactant, and so the reaction is going to want to get rid of the extra reactant, and now it will move towards the products. Does that make sense? Can we now talk about why? You ready for this? Guys, let's go over here and talk about our first example. In this example, Q is bigger than KC, right? So if Q is bigger than KC, what do we have too much of? Reactant or product? Too much product. Why would that make the reaction go to the left? No. Okay, stop. That's what I wanted you to say. Guys, did you hear what Mark said? I said, why would that make the reaction go to the left? And Mark said Le Chatelier's principle. If you write that down on the test, you're sunk. Because chemical reactions have never heard of Le Chatelier or his principle. It describes what happens, but it doesn't explain what happens. So guys, what explains why the reaction will go to the left? It's collisions and the rate goes up. Guys, if you've got extra product, you've got extra product. And if you've got extra product, that extra product collides more frequently and it increases the reverse rate, turning reactant into product. But we know that that reverse reaction is always then slowing down and eventually the rates restabilize back at equilibrium. Go ahead. Mm-hmm. Extra product molecules. Uh-huh. Right. Yep. When they start banging into each other with more magnitude and frequency. No. That's temperature. It's not it's not magnitude. It's just frequency. There's more of them. They collide more. They're not moving faster because it's the same temperature.
Okay. But it speeds up the reaction.
Correct.
With the product decomposing into the reaction.
Well said. Yes.
When it's the reverse, when Q is smaller than KC, reactant.
Then you've got too much reactant, and it goes the other way. Yep. You guys get the idea? So let me offer this to you by way. Oh wait, Rebecca, you've been waiting forever. Go ahead. Yes. No, good. So here's the great question. So Rebecca's question is, if we're not at equilibrium, can we draw the equilibrium arrows? And the answer is absolutely, because technically the double-headed arrows don't mean at equilibrium. The double-headed arrows means reversible. And that applies regardless of whether it's at equilibrium or not. You guys okay? Okay, so guys, if you want this, knock yourselves out. If you don't, that's fine too. But guys, oh gosh. So here's the idea, like so. So guys, this idea of Q. So Finally, we can use k-values to predict directions that reactions will proceed. To do this, we plug in concentrations that are instantaneous. They're not at Kc. They're not at equilibrium. We call this Q, which is the reaction quotient. So Q and K are the same at equilibrium. At other conditions, the relationship between K and Q allow you to figure out the direction the reaction will proceed. Do you want to write this down, or are you okay? So it goes like this. If Q is bigger than K, the reaction will go to the left because you've got too much product. If Q is smaller than K, the reaction will go to the right because you've got too much reactant. Everything that we just said. So guys, we're done. We have, bless you, 10 minutes. So let me go back and give you your homework. Please remember, guys, I will see you A2, but I will not see you A3. Gilchrist is going to come and grab me, and if I resist, he will beat me up. So, guys, you'll have a sub. I don't know who it is. You'll just be watching the screencast of me teaching this last year. And then on Tuesday, when I see you again, we'll be grading 2 homework assignments and then going over the math of equilibrium, and that'll be our day. So guys, here's the homework again. Now all of this is in play. But again, guys, we're not going to grade it until Tuesday.